This is Keith Devlin, Chief Scientist at Brainquake. This short video provides a quick overview of the products we developed using our SBIR awards. In Phase 1, we built an adaptive engine that would deliver our math learning and assessment puzzles at the appropriate difficulty level. We first implemented it in our existing math app, Was It Trouble? This app was built on integer arithmetic and integer partitions to develop number sense and mathematical thinking ability. Like all our puzzles, the original Gears puzzle was designed to break the symbol barrier, providing an alternative representation of the mathematics. In this case, linear equations in up to 4 unknowns. Independent university studies had shown it to be effective, but the extremely wide range of puzzle difficulties implied that an adaptive engine was required to select puzzles at the right level in order to ensure that students remained in their zone of proximal development. Our proprietary adaptive engine was tested in schools by our research partner West Ed towards the end of Phase 1 and found to be highly effective, as described in their Phase 1 feasibility report. In Phase 2, we developed 2 new puzzles. The first I'll describe, Tanks, focusing on fractions and proportional reasoning. The player moves up to 4 arms to apportion a liquid from an input tank so as to exactly fill 2 or more output tanks. After the player thinks she has set the arms correctly, she presses the fill button and liquid flows to the output tanks. This one is an early example for the player to become familiar with the mechanism. This one is a bit more tricky. You have to fill it in 2 steps, changing the arm positions after the first move. The video doesn't show that the fill button is pressed, by the way, but it is. More complicated puzzles show labels, such as fractions. There are different shaped valves. This rectangular valve has percentage labels. Some rectangular valves are subdivided by vertical arms. There are also valves of other shapes not shown in this video. So far, I've got them all right. Let's see what happens if I get the math wrong. A tank overflows. I hit try again, and this time I'm a bit more careful. Only 2 stars instead of 3, since it took me 2 tries. With 3 output tanks, the puzzles can become more challenging. We also have labels that are decimals between 0 and 1. This one takes 4 applications of the fill instruction to complete. With all puzzles, the input tank immediately refills when it is emptied. Puzzles with 4 output tanks are the most difficult. Throughout the game, the player is presented with proportional reasoning tasks with different symbolic representations and different spatial representations. The idea is that by playing the game, students gain a deep understanding of fractions and proportions. Classroom studies carried out by our research partner WestEd have confirmed that this is indeed the case. Our other new puzzle developed in Phase 2 is Tiles, an algebra puzzle. In this puzzle, the goal is to place growable tiles in one or more trays so that, when they all grow, they exactly fill all the trays without overlapping. The tiles have chevron markings that indicate how many squares they grow by in that direction when the player presses the Grow button. This one is a bit more tricky. Though there's still only one tray, you have to select which tile or tiles to use as well as where to put them. The tile chosen grows 2 to the left and 3 to the right each time. To fill the tray, you also need to put a constant tile at the right end. Then 2 grows completes the puzzle. Because I solved it efficiently with the fewest possible number of grow moves, I get a chance to earn a bonus item by finding a solution with the fewest possible tiles. After some thought, I realise I can do this by using a tile that grows just 1 step each time. Other puzzles where there is a bonus item can be more tricky. Here's a puzzle with 2 trays. As you move through the game, you reach puzzles with 3 and 4 trays and many tiles to choose from. As with the gears and tanks puzzles, the adaptive engine always selects puzzles that are challenging but doable. Studies have shown that the adaptive engine actually forms a pretty good assessment of an initial performance level after only 10 to 15 puzzles, but it monitors performance throughout. The tiles are representations of linear equations, but unlike gears, where the focus was on solving equations in several variables, with tiles we concentrate on linear functions as a way to describe growth processes. Solving a tiles puzzle involves solving a system of linear equations in a single unknown. To present this challenge in an engaging way, we incorporate an element of spatial reasoning in the positioning of the tiles. As with all our puzzles, the primary goal is not to develop algorithmic skills of performing symbolic mathematical calculations. Rather, we use certain mathematical topics as a basis on which to build engaging and challenging interactive learning experiences to develop number sense, mathematical thinking capacity, and general problem-solving skills, while avoiding the symbol barrier. Having said that, however, we expect that many students and teachers will want to use the skills they develop solving our puzzles as a basis on which to master the traditional, specific skills. To assist making the transfer, which is well known to be a difficult step, another goal of our Phase 2 project was to design and build what we call digital manipulatives that more explicitly connect the puzzles with the underlying mathematics expressed in a traditional fashion. Here is the digital manipulative for the gears puzzle. As you'll see, as the student solves the puzzle, the corresponding equations appear on the left. Since the aim of the DM is to develop the ability to do accurate symbolic computations, it asks for correct answers. If you get it wrong, you have to start again. The DM puzzles are fairly simple ones. Playing the regular gears puzzle provides plenty of difficult challenges. The aim of the DM is to make the connection between the 2 representations at a very basic and fundamental level. This puzzle requires 2 steps to solve. Unlike gears and tiles, with the tanks puzzle, the connection with traditional mathematical representations is self-evident, and the DM focuses on using the tanks mechanism to develop an understanding of the many different ways there are to talk about fractions, something that is known to cause problems for 1 in 5 adult Americans. The idea is to use the tanks mechanism to answer the question at the bottom. The colours connect the question with the mechanism. We have made this discrete so students can count up squares to gain a deep understanding of the various proportions. The student or teacher can select between different ways of expressing proportions. To answer the selected question, you use the tanks mechanism. Do I think the answer is 35%? No, that's too little. I can check by counting squares. Try again. Maybe it's 86%. No, wrong again. This time it's too much. I can see what went on by counting squares and comparing what went where. Try again, and this time I'll be more careful. I set the arm at 75%. I can watch the transfer step by step and can also count up what proportions are transferred and what proportions are left where at the end. In particular, the input tank has 1/4 remaining and 3/4 have been transferred to the output tank. And I can check again to see the different ways to describe this transfer. The tanks DM also presents problems going the opposite way, where the valve is preset to a specific percentage and you have to say what size of input tank will exactly fill the output tank. Suppose I think the answer in this case is 160. No, that's too small. Try 180. That time I get it right. Our third digital manipulative is for the tiles puzzle. The goal here is to build your own tiles and predict in advance how they will grow step by step to fill a tray. You begin by dragging square tile elements to create a tile up to 4 wide, as in the tiles puzzle. I'll create a tile of width 3. Then I drag chevron markers to create the growth rules for my tile. I decide to make it grow 1 to the left and 2 to the right. So I've represented the function 3x plus 3 as shown above the tile. I now drag my tile into the tray. The system will always provide a tray that the tile constructed will fill. Again, the purpose of the DM is not to help anyone solve the real puzzle, nor to master algebraic manipulation skills, rather to understand how the puzzle connects to the traditional algebraic representation of linear growth functions, to help facilitate transfer. Next, I have to mark the positions the tile ends will be at after each grow move. I cannot proceed until I have entered them all correctly. That looks right. Now I hit Done. A table appears that will track my solution using traditional equations and populates with the initial position when x equals 0. The y denotes the width of the tile. I hit grow, and as the tile grows, according to my rules, the new value of the function for x equals 1 appears in the table. I hit grow again, and the value of the function for x equals 2 appears. It's 9. Notice the colour coding that links the tile's situation and the table. One final grow, and the tile fills the tray, and the function value in the table is y equals 12 for x equals 3. I could have created a tile with initial width 1. What I cannot do is create a constant tile. The focus of the DM isn't on the tiles puzzle, but on linear growth, bringing out the way the puzzle provides an interactive way to experience linear growth patterns in the course of solving challenging and stimulating quantitative and logical problems of mathematical thinking. To end this video, let me touch on one more project deliverable: our proprietary Brainquake score, a triple of numbers measuring performance, how well the individual solved all the puzzles, persistence, the degree to which the individual displayed what some people call grit, and creativity, the degree to which the answer showed ingenuity and creative thinking. This is in fact the score I got after I'd played enough puzzles to capture clips for this demo video. You can tell that from the score. Since I deliberately got some wrong to capture the game's responsive, I scored only 90% on performance, even though I never got as far as the difficult puzzles. Creativity of 24% is lower than I would normally expect, but with earlier, simpler puzzles, which I was playing, there's not much opportunity to exhibit creativity. Likewise, I never got to a stage where I would struggle to find a correct or optimal solution, so the algorithm had no data to calculate my persistence index. But because the more advanced puzzles can be very challenging, even though I developed them, I always find some of them quite a struggle. So if I were to continue playing, the algorithm would generate a meaningful Brainquake score for me. In general, the more someone plays through the game, the more meaningful is the Brainquake score they earn.